Welcome back everyone to the second video of our AP Calculus BC series. Today's topic is on estimating limits. And in our last video, we developed an intuition for limits and we played around with a little bit of estimating limits. But in this session, we're going to formalize or do more practice with estimating limits. So the first skill that you'll be required to know as per 1.4 is estimating from tables. So generally, you're going to be given a table of x and f of x in the neighborhood of an important value. And in this case, that important value is x equals 9. And the limit as x approaches 9 is sort of the key information that we're trying to figure out from this table. Here we have the right-hand side, the left-hand side, and the actual limit. Really though, because this is estimation, you can't get too precise with the values, and often intuition is enough to do the job. So here for the right-hand limit, we look at the x values first here. We are getting closer and closer to 9 from the right-hand side here. And in terms of the f value, we get 2.3, 2.01, 2.001. And so it's really clear that this is getting to 2. There's no real way we could justify this because there are just so few values and information given from this table. But 2 is definitely good enough of an answer. So we're going to say the right-hand limit is 2 here. Now, from the left-hand side, we're going to do the same process, 8.9, 8.99, 8.99. We're getting closer and closer to 9 from the left-hand side. And if you look at the values, 0.7, 0.8, 0.999, we are getting to 1. So these are the right and left hand limits. And as covered in the last video, the actual limit's existence depends on if the left and right hand sides exist and agree. And in this case, they both agree, they both exist, but they don't agree. So therefore, this does not exist, D and E. This is the first time we've used this notation because we didn't give enough examples last time, but DNE means does not exist. This could also be for left or right hand limits. For example, if it's positive infinity or negative infinity, we also write does not exist, or if it's oscillating, as mentioned. Okay, so now in this example, we are asked to make our own table for estimation. This type of question doesn't appear on the AP exam, but it's good practice and great for intuition building. So we're going to do an example here. Actually, it would be more convenient if there are 6 cells, so let me add one here. We're going to do this estimation in a similar fashion to the previous one. We're just going to go with minus 0.1, so this is going to be negative 2.1, negative 2.01, negative 2.001, and negative 1.999, negative 1.99, and negative 1.9. And we're going to see what these values give for the function. Here I used a calculator. Remember, on the exam, you are allowed to use a graphing calculator. We will be making videos on how to use a graphing calculator later. And knowing how to use this is really important. Alternatively, you could have noticed that this is equivalent to x plus 3 whenever x is not equal to negative 2. And so here we have this table of values, and we're going to do the same process as the previous one. So we're going to first consider the limit as x approaches negative 2 from the left-hand side. Here, we're going to trace the table from the left-hand side. And it's clear that 0.9, 0.9, 0.99, 0.999 gets closer and closer to 1. Then similarly, we're going to calculate, we're going to actually estimate the limit as x approaches negative 2 from the positive side, which if we follow along here, 1.1, 1.01, 1.001, this also gets closer and closer to 1. And so therefore, because the left and right hand sides exist and agree, we can find that the limit itself, as x approaches negative 2, is equal to 1. And so we have completed an estimation via a table. So now we're going to move on to estimation from graphs. The general method we're going to use here is, as previously done, we're going to trace along the graph from the left and right hand side. as to determine the left and right hand limits, and then we're going to determine if it exists, the limit, determine if limit exists and what the value is. And just as review, last session we covered the conditions under which a limit exists. So a limit exists when both left and right hand exist, right hand limits exist and agree. So now using this methodology, we're going to look at a couple examples, some important limits where the limit does not exist. And we're going to see what types of conditions might constitute a does not exist. So starting from here, we want the limit of 1 over x squared as x approaches 0. So we're going to trace along the graph to 0 from the left-hand side. And it's pretty apparent that this goes to positive infinity. And from the right-hand side, it also goes to positive infinity. And so both the left and right hand limits tend to infinity, and therefore both do not exist. So positive or negative infinity, as mentioned previously, they make a do not exist. And so because at least one of the hand limits do not exist, this whole limit does not exist. So we have found the first way in which limits do not exist is if a hand gives positive or negative infinity. So like if a left or right hand limit gives infinity, a hand limit, I'm just going to call that. Okay. Then again, it's the tracing idea. From the left, as we approach x equals 0, from the left we get this limit is equal to -1. And from the right hand side, it is equal to 1 just by tracing. We see that the values or the limits on both hands exist, but they disagree. So they disagree, and therefore the limit does not exist. So this is a second way in which limits don't exist, and it is if the left hand and right hand limits disagree. Okay, so moving on to this limit over here. This is a classic example of oscillation. And here it's really not traceable, and therefore like it makes sense that this does not exist. And we're going to go into a little bit greater detail. So we're first going to consider the right-hand limit of this expression. And we're going to notice that as x tends to 0 from the positive side, 1 over x tends to positive infinity. This just makes sense because as you get smaller and smaller in the denominator, you're going to get larger and larger values. And this unboundedly large value, you want to take the sign of it. And so therefore, when it gets closer and closer to 0, it's going to fluctuate like crazy. And so therefore, this is a classic example of an oscillating limit. So it oscillates, and so therefore it does not exist. It's too unpredictable. And so this constitutes our third way in which a limit won't exist. So you could also run the same analysis from the left-hand side, right? But one side is enough. Here we have the classic 1 over x. I'm not going to elaborate too much on this. From the right-hand side, it's positive infinity. From the left-hand side, it is negative infinity. And so therefore, this is just the first type. Okay, so just to recap, the three ways are if there's a positive or negative infinity on either side, if they both agree and if they both exist but disagree, or if there's an oscillation. These are the three primary ways in which a limit does not exist. Okay, so following the same method, we are going to take a look at examples where the limit does exist. So here, we want to first find the limit of f of x as x approaches -1. So here we have -1, and we want to consider what happens to f as x approaches -1. So we're actually going to do some estimating on the graph at first, and we're going to guess that this point is around -2. And this point corresponds to a -1. So as we go, we're first going to consider what happens on the left-hand side, just to be a little bit more systematic. So from the left-hand side, we're going to go up and up, and it does seem to tend to -1. And here on the positive or the right-hand side, we have something similar. So it's just -1. They agree, and therefore this gives a limit of -1. So this gives a limit of -1. Okay, the limit of f of x as x approaches 3 from the positive side. And so for this one, we just trace it along this. Notice this is 3. We trace it along here. We don't care what happens here. We only care what happens like here, right? Immediately close to 3 in the closest neighborhood. So here it seems to tend to 0. Okay, the limit of f of x as x tends to 0. Oh, so here we have from the left-hand side, we have what seems to be 0. And from the right-hand side, we tend towards 3. And so this is an example of type 2, right? So they exist but do not agree. So therefore, this limit does not exist. Okay. The graph of g is shown below. We want to approximate the following values. Again, it's the same idea. So we want 4 from the right-hand side. This seems to tend towards 5. From the left-hand side, this tends towards 3. And so therefore, again, both exist, don't agree, so therefore the limit does not exist. Okay, this is the exact same. So here we have from the positive side, or from the right-hand side, that gives us -2. From the left-hand side, that gives us 3. The limit altogether would not exist, again, because they disagree. And the value of f itself is 1. So notice this again shows how the value itself is completely irrelevant to the limit itself. So here we have this problem where we're required to draw the graph by ourselves. And this function here is the floor function, the greatest integer that is less than or equal to x. And we want to find the limit of this as x approaches 0 from the left-hand side. So we are looking in this direction. And what we first want to consider is that the floor of x is always equal to -1 when x is in the interval of -1 to 0. So this is key to graphing this, and we would notice that, so therefore over this interval, this expression, so 2 over floor of x, would then equal to -2. So we find that over here. So from -1 to 0, you're going to have that this function looks like this. And this is actually the only segment that we need to care about, because as we approach from here, the value of f of 0 itself does not matter, and we only care about what it tends to. And it's just very clear that except for this point, everything before it suggests that this would be -2. So this is our answer. Okay, it's all right. I know what's in that text above. So basically, we are given the functions f and g, and we know that there's a vertical asymptote. So this is a vertical asymptote of x equals 2. And we are given a table of g. So using this information, we first of all want to find the limit of f as x approaches 1. So here we're going to use the same method. We're going to trace for the left and right hand limit. The left limit is 4, and the right limit is also 4. So these values exist and they agree on a value of 4. So that is our limit. Then for this next one, we just again examine the left and right hand side. The left side suggests a 5 and the right side also suggests a 5. So the answer is just 5. I'm going a little bit faster here. For this next limit over here, we're first going to skip over it because the most rigorous way to do it is just to graph f of x, and that takes a lot of time. I would encourage you to try to draw this yourself and deduce this limit. Finally, we want to find all c such that this limit does not exist, and that basically means looking for two things. One is where the limit, or like the left or right hand limit, does not exist, and or where they disagree, right? So here, most obviously, we have that at x equals 2, we have that the left-right limits do not exist. This is quite obvious. It's positive and negative infinity. Then here, at x equals 0, we have a disagreement. At x equals 1, though, the limit does exist, as we've shown previously. So there's no problem here. And pretty much everywhere else, we can't find instances of where the left or right hand limits do not exist, or if there's disagreement. So these are our only c's. So c can be equal to 0 or 2, and that is our answer. And so that is it for today's video. In our next video, 1C, we'll be talking about determining limits. And that would not require a graph or a table. We can just use algebra to figure out the exact limit. And usually this is the most efficient method. So next session is going to be very important. Thank you very much.